When you came in, we have pretty pictures for you. This one tonight's is of the Cat's Eye Nebula, also known as NGC 6543. If you didn't get one on the way in, they're on this side and on this side. I've gotten smart as of late, putting them on both sides. And if you want to know more about it, turn over. There are about 300 words on the back to tell you all about it. Yes?
The sound seems out of phase.
Okay. Is it coming? Am I getting both mics?
Yeah.
Let me try that. How about that? That better?
Yes.
All right. Thomas, we okay? All right. Thomas is okay. He's changed things over there. All right. Our speaker tonight, Worldwide Telescope Around the Universe in 80 Ways. Frank Summers from the Space Telescope Science Institute. I've known him quite a while. He's a pretty good speaker, I think. Upcoming next month, Margaret Meixner, The Life Cycle of Dust in Galaxies. We often think about dust as being something that we don't like around the house. We love it in galaxies. There's all sorts of cool stuff to talk about that. In September, Tom Brown, who was nice enough to postpone his talk so I could bring in a speaker in May, On the Trail of the Missing Galaxies, the Oldest Stars in the Neighborhood. And in October, Bill Blair from across the street at Johns Hopkins. He hasn't given me a title, but he's given me a topic, supernovae. He'll figure out exactly what topic it's going to be pretty soon. For those of you watching on the webcast, if you decide to come down and join us, recognize that the San Martin Drive south of the Institute is closed until approximately September. So you must approach STSCI from the north. Those of you who are here already know this. Our website, if you just put into your favorite search engine, Hubble Public Talks or Public Lectures, you should find us. We also at hubblesite.org have a Go Talks link for it. On this, you can we have the list of the upcoming lectures. All right, we have the webcast, the live ones when it's live. The archives, we have all the way back in the STSCI webcast archive back to 2005. We've got stuff on YouTube back to 2014. And you can also subscribe to our email list. Okay, actually this has been great for us. We've gotten a lot of people on our email list that has really helped get the word out for things. If you would like to use the old-fashioned way, you can go to maillist.stsci.edu. You look for public lecture, announce, and provide, and sign up there, or you can just give me your email address at the end of the talk, and I'll add it in. All right. If you would like to contact us, our email is publiclecture@stsci.edu. Comments, questions, like this gentleman had a question he thought of after the talk last time, send it to this email. We'll try and answer them. All right. If you do social media, we are on Facebook and Twitter and Google Plus and Pinterest, and I'm on Facebook, Google Plus, and Twitter. And here are the references should you want to follow us. The observatory across the street. We have some new folks here tonight. The Maryland Space Grant Observatory runs this telescope on the Physics and Astronomy building across this street. The email I got from Duncan said that the weather looks good and it will be open tonight. That is, of course, subject to change. Astronomy is always subject to the weather. We'll make an announcement at the end, checking to make sure Duncan is here. Weather permitting. If it doesn't happen tonight, you can go to md.spacegrant.org. They run observing nights, I believe, every Friday. Okay? All right. And now, our news from the universe for July 2016. Since I am the speaker as well as the host tonight, I'm only going to give you one story, but it's a really involved story here. So tonight's Juno arrives at Jupiter. Okay, so yesterday, the Juno mission, after a very circuitous route through the solar system, finally arrived at Jupiter. And this is an artist's impression of the spacecraft of Juno. It looks sort of like a three-pronged helicopter blade. All right, these are all the solar panels. Yes, it is out at the distance of Jupiter, 5 times further away than Earth. 1/25th the solar radiation, but it's still using solar power to power the spacecraft. All right, and it's approaching Jupiter, and you notice that you only see half of Jupiter. okay, because it's going to fly into Jupiter sideways and go into a polar orbit, okay? It's going to be orbiting around Jupiter in a polar orbit. The main purpose of Juno is to study the atmosphere and the magnetosphere of Jupiter. The magnetosphere of Jupiter is the largest structure in the solar system. If you could visualize it, it would be like 3 or 4 times larger than the full moon on the sky. Okay, it's a really huge structure. All right, Jupiter has an incredible magnetic field. And actually, I did my little motion here wrong. It's actually going to have a very elliptical orbit around Jupiter. So it goes in deep into the magnetic field and goes way out in the magnetic field to sample all of the magnetic field. Okay? And here is the pole of Jupiter where there is an aurora that can be seen in the ultraviolet. Now, this spacecraft has on it ultraviolet and infrared science cameras. It does not have a visible light science camera. So if you're thinking this is going to be like the Galileo mission, which got lots of really cool pictures of Jupiter or Jupiter's moons, that's not the intent of this mission. Okay? The science that we don't know about Jupiter is really heavily involved in its atmosphere, atmospheric structure, and magnetosphere, and that's what it's designed. But it does have a small visible light camera that they put on called JunoCam. It's 1600 by 1200 pixels, so it's really similar to about the resolution that you would have on your camera phone. And they have allocated a certain amount of bandwidth for that camera, so you will get some visible light pictures, but most of the pictures you're going to get from Juno are going to be infrared and ultraviolet, as well as a lot of magnetosphere data. So if you're into magnetospheres, this is the mission for you, okay? But that doesn't mean there won't be some fun pictures, okay? And so they released these pictures in the last couple weeks. This is an actual shot from JunoCam, and you see that's edge-on view of Jupiter, and you also see these white dots. Well, these white dots are, of course, the Galilean moons, Io, Ganymede, Callisto, and Europa. All right, and they released a movie of the approach. And you can actually see the Galilean moons orbiting around Jupiter. Now, if you watch over here, you'll see them blink off. Why are they disappearing? They're hiding in Jupiter's shadow. Okay? Kind of cool to sit there and watch the moon's orbit and actually see them disappear when they go through Jupiter's shadow. Now, when NASA puts this kind of money into a mission and sends it over several years out to Jupiter, all sorts of other telescopes are there supporting it. I believe there's like 17 different telescopes that have done Jupiter observations in support of the Juno mission. Some really cool ones came out from the European Southern Observatory. Now, this is not an ESO image. This is an, again, I hate to call this guy an amateur. Damian Peach is one of the greatest astrophotographers out there. He took this gorgeous picture of Jupiter about the same time as the ESO, the European Southern Observatory telescope, took this image in infrared. Kind of cool. All right? So these two images were taken of Jupiter at about the same time. All right? And so this is visible light. This is 5 micron infrared. Okay? So this is where the heat in Jupiter is coming out. Okay? Where it's bright is where you're seeing infrared light emanating out of Jupiter. And one of the things I find that's really kind of cool is that what's bright in infrared appears relatively dark in Jupiter. Not always, but there are some examples. So, can you see these little dark circles here in the visible light image? Well, they're bright circles here in the infrared image. Conversely, down here where you've got these white ovals, these bright features in the visible light image, they appear dark in the infrared image. So by using multiple wavelengths of light, we can study different layers and different depths in the atmosphere and the different energetics that's going on in Jupiter's atmosphere. But one thing I'd like to highlight is how they got this clear of an image of Jupiter from a ground-based observatory. And they did it by a process called lucky imaging. All right? So, watch this carefully. This is a movie, all right, of many short exposures of Jupiter in the infrared. They took a lot of very short exposures. Since Jupiter's bright, they can take some short exposures. Okay, whoops, that wasn't what I meant to do. Let's go back. There we go. Here's the movie. Okay, watch carefully. All right, and you'll see the resolution change. Sometimes it's clear, and sometimes it's fuzzy. All right, and there was a fuzzy patch, right? The atmosphere, Earth's atmosphere gets in the way, right? So going through that, they go through the individual exposures, and they find the good images and the bad images. Okay, and let me just blink those. I'll switch them, and you can see the difference, right? All right, so when the atmosphere is not in your favor, you get some fuzzy images. When it's just perfectly clear, you can get it good. So they take all the good images, they co-add them together in order to make their images. This is a new technique that has come about in the digital era, that if you take a lot of very short exposures, you can combine them, all right, and be able to get higher resolution than you normally would if you took one long exposure. All right, and so this is there's a number of new techniques that allow us to get higher resolution from the ground that weren't possible 10, 15, 20 years ago. All right, now the European Southern Observatory is not the only telescope supporting the Juno mission. The Hubble Space Telescope did also support it, and Hubble has, being above the atmosphere, can observe in ultraviolet, and so it can observe that aurora on Jupiter. And so it took many pictures of the aurora on Jupiter and was able to get this movie. That's the activity in the aurora on Jupiter over the course of an hour or two. Okay? I actually know it's over one orbit, so that's about 45 minutes. All right, let me play that again. That was just really cool.
What you just played was 45 minutes worth?
Yes, about 45 minutes worth of the aurora on Jupiter.
I got you.
All right, and you see this spot right here? That spot is due to the moon Io, because Io has tremendous volcanism spewing sulfur dioxide into the space around it. That gets caught into the magnetic field and streams in and slams into Jupiter's pole. All right, and that's the Io spot. There's another spot that's due to Europa and another spot that's due to Ganymede. Okay, so the interactions of the moons with Jupiter's magnetic field show up in the aurora. And another cool thing is that you can take that, and we said, well, this is nice in the ultraviolet, but people want to understand what it really looks like. So we took the ultraviolet, we composited it onto a sphere of Jupiter. Now, these are not coincident observations, okay? The other ones I showed you with the infrared and visible, those were coincidence. This is just a model of Jupiter that we had, texture map, but we wanted to show you what it looks like if you put that in motion. So here's that same movie, but with the reference scale of Jupiter underneath. And this, a still from this already appeared on Wikipedia on the magnetosphere page. So when Hubble releases something, it gets lots of attention. All right, so Juno has just gone into orbit. I'm sure they've got some the instrument checkout that as you always do after arrival, and we'll start to get results from Juno probably this fall. As I said, they won't be the gorgeous pictures that you got from Galileo, but they will nonetheless be cutting-edge science studying the atmosphere and magnetosphere of Jupiter. All right, now we get to our featured speaker. Many of you know me. I've been here 15 years at the Space Telescope Science Institute. I've been running this public lecture series for 14 of those 15 years. And so it's hard for me to come up with something new. Basics, I got my undergraduate degree at Virginia Tech, got my PhD at Berkeley. I did postdocs at Princeton and Columbia, yada, yada. Okay. The one thing that I found out that's cool about me is I have my niece visiting me, okay? And she came and she heard me give a lecture. And the one thing that she said, oh, that's cool, was that I happen to have a Guinness World Record, okay? All right, and it's not just I have the world record, I'm in the book. All right, so this is the official Guinness World Records 2014, and at the 2013 South by Southwest conference, Dan McAllister and I, pictured right here, okay, set the Guinness World Record for world's largest astronomy lesson, okay? Now, the world's largest astronomy lesson, Guinness has rules. It has to be outdoors, has to be at night, and has to have an educational plan associated with it. All right, and with the outdoors and at night, I mean, people give astronomy lectures at Berkeley that are, 1,000 people, right? So the record at the time was only about 400 people. We set the record with 540, 550 people. I hate to say it has been broken since 2013 by a group, I think in Australia, that got on order of 1,000 people. But for a couple years, I was world record holder, Guinness World Record, and I find that my niece tells me that's the only cool thing about me. All right, so let's switch over to my other talk.
Ladies and gentlemen, Dr. Frank Summers.
Oh, thank you very much. There we go. That's a proper introduction. All right, so tonight we're going to talk to you about WorldWide telescope, and I call this Around the Universe in 80 Ways, okay? It's a piece of software that does amazing and incredible things, yada, yada, yada. Most of this talk is going to be a demo, all right? So I just have a few slides to set this up. All right, so this project started out at Microsoft Research. It was inspired by this man, Jim Gray, a winner of the Turing Award, which in computer science is sort of like the Nobel Prize of computer science. He won the Turing Award in 1998. He's working at Microsoft Research doing e-science, solving scientific problems that require huge, huge data sets, okay? And he works with astronomers, and he has these cool ideas. He inspired this project, which was executed by Curtis Wong over here and Jonathan Fay over here. This is the symbol of WorldWide telescope. Well, these guys got started in 2007. They contacted us mid-2007 to start saying, hey, if you're going to have cool data, you want Hubble data in there, of course, right? So we worked with them to get Hubble in it, but they quickly moved on to just about everybody in the astronomical and earth sciences community. Here is the current acknowledgments on the website. You can see it's just all over the place in terms of the amazing number of people they worked with to get an astronomy exploration tool off the ground. Well, they also inspired us to take projects that we had started in outreach and sort of push them forward. In particular, this VAMP project, the Virtual Astronomy Multimedia Project. We have a problem in outreach. When we produce that beautiful Hubble image, we've lost track of all of the scientific data behind it, okay? Because, when you produce a JPEG image, it doesn't have all the science data in behind it. Particularly, the coordinates of that image are lost and where it is on the sky. Well, VAMP was a project that we had started in 2003 or 2004 amongst the major observatories, and we hadn't really pushed it forward. WorldWide Telescope gave us a great impetus for really pushing it forward to create AVM, the Astronomy Visualization Metadata Standard, okay? And basically so you could put all that data back into these public release images. That also led to the creation of AstroPix, which was a website where people could share these images that had been tagged with AVM metadata. All right, so that you have all of these images. So for example, if you've got the radio galaxy Centaurus A here, you can go to its web page on AstroPix, and you can download these images. All of these images have the AVM data in it, okay? And that AVM is tagged, and then you can use it in WorldWide Telescope. It also allows major observatories, like, for example, the Hubble Space Telescope, to take their gorgeous images here, all right? And if you scroll down on this web page, you can see that it's got coordinates, as well as view this in WorldWide Telescope, so that the images from major observatories can be tagged with this metadata, and then makes it much more useful for the public to bring them in. I hate to admit it, but this is only available on the ESA version of the Hubble Space Telescope site. The folks here have been understaffed in terms of getting this onto our website. Hopefully in the near future that will be fixed. It also brought about groups who said, this is such cool software, we got to get it out to the public in lots and lots of different ways. In particular, the WorldWide Telescope Ambassadors Program, which is based out of Harvard. Alyssa Goodman runs it up at Harvard. And in terms of trying to get things first to educators, but also out to science fans, and the ambassadors themselves are the scientists, the astronomers who want to work with educators and work with the public using an easy-to-use tool out there. So there has been a lot of really cool offshoots within the astronomical community from this software. It has been used in all sorts of fun places. Here I am giving a talk at the South by Southwest conference. That was the 2013 conference where I set the world record. Okay, this screen here is a 30 million pixel screen that Microsoft put together, and we had to make special extra widescreen tours to work with that. Here is the WorldWide telescope on the dome of the Adler Planetarium in Chicago. So the software has been adapted to run on planetarium domes. And here is a gentleman enjoying WorldWide telescope while using the Oculus Rift virtual reality. So you can strap on an Oculus Rift and just really go space out, right? Okay. The story, however, doesn't end there. The story had a few twists and turns. Curtis Wong went off to other projects, so Jonathan Fay was left in charge. Very capable guy. Best programmer I've ever met in my life. However, in September of 2014, Microsoft Research restructured and funding for the WorldWide Telescope project ceased, and the project was sort of in limbo. Then Microsoft decided that they would open source WorldWide Telescope, which is, really nice, okay? I mean, this is not in Microsoft's nature to open source a really nice piece of software like this, but because it came out of Microsoft Research, perhaps, they're able to open source it. So at least the data, the software didn't go totally into limbo, but we needed an organization to step up to say, okay, we'll take control of it. And in January of this year, the American Astronomical, whoops, what happened there? There we go. I don't know why. There we go. In January of this year, the American Astronomical Society stepped up to the plate and they became the institutional home of WorldWide Telescope. And you can see this is the AAS logo. So somebody took the star here and went, boom, there we go. That was a nice thing. The American Astronomical Society wants to not just use this as an outreach tool, they want to use it as a research tool in association with the research journals, the Astrophysical Journal, the Astronomical Journal. The idea being that astronomers have lots and lots of data, images as well as data sets that they need to pass on to their colleagues or their other colleagues want to work with. How do you pass on digital data in a print journal? All right, well, you try and do all these things, but the WorldWide Telescope actually becomes a way in which one can take that astronomical research level data and pass it on to your colleagues and have them have an easy way to look at it and use it. I'll give you a couple examples of that tonight. So this is the current web page for WorldWide Telescope. It is simply worldwidetelescope.org. Okay, you can see it's already branded with the American Astronomical Society as the institutional home. Now, coming out of Microsoft, as you might expect, there is a Windows application. It's free, okay? I will emphasize that it's free, okay? But it only runs on Windows. And you say, oh my gosh, how can I handle that? I love Macs. Well, I'm on a Mac, okay? There is an HTML5 web application. And if I exit out of this, I can't show it to you on this, can I? Because I'm not mirroring the desktop. Let me just show you on my iPad, okay? All right. All right, let me pull it up on my iPad. There we go. All right. There is WorldWide Telescope running on an iPad, okay, and Safari. All right, it also runs under Safari and Firefox and Chrome on iOS. HTML5 is the lingua franca of the web, so it'll run on Linux as well. All right, there is one major thing you can't do with the web client, and that's create tours. All right, you can play tours, but you can't create them with the web client. I'll show you stuff about that tonight. That has to be done unfortunately, with the Windows application. All right, so that's the background of WorldWide Telescope. Now let's get into the fun, the meat of it, and we will switch over to my Windows laptop. There we go, and show you WorldWide Telescope. Okay. There is so much to show you. I actually had to create myself a script, okay? So we got a lot of things to go through here tonight. All right. So this is WorldWide Telescope, is there a way we can, the screen needs to be really dark. Can we take the lights down just a little bit further? All right, because there's just real subtleties on the screen. All right?
Are you picking up on 2 mics again?
As far as I know, I'm only on one mic. Is that working? All right, there we go. Okay, so you can explore the night sky by panning across the night sky. All right, and we can find the constellations. Anyone recognize this constellation here? Orion, yes, okay. And if you mouse over the bright stars, usually it works. There we go. That says Betelgeuse. And down here, this one is Rigel. Okay, although it says HR or something else. It doesn't have the Rigel name, okay? We come across here, continue moving. Oops, there we go. That's what I'm looking for. Leo. I should look at my own laptop. It's easier. We're looking at the constellation of Leo. Okay, we can pull across until we get to the Milky Way going across here. All right, and then we get to a famous asterism that we hear. That's got Deneb here, and Vega here, and Altair down here. That's called the Summer Triangle. All right, now I know this is Cygnus, but if I didn't know, if you look down here in the lower right-hand corner, you can see it says Cygnus, and it shows you the outline of the constellation of Cygnus. So really helpful in terms of looking for those constellations. We can go up, and we can find the Big Dipper here. And if you've got the pointer stars, right, these pointer stars point toward the Little Dipper and the North Star Polaris. And if I go up here and continue, we start to spin. Why are we spinning? Okay, we're spinning because, of course, we are in equatorial coordinates. All right, and so I can go over here and turn on some grids. Okay, and I can show you the equatorial grid. All right, and this is the equatorial grid overlay. This is your layer manager here. All right, and that shows you that the Polaris is very close to 90 degrees north. Okay, it's actually like 89.5 degrees north or something like that, but it's very, very close. All right, and so the equatorial grid, you can work down and come down to the south and find that there is no South Pole star. Okay. It makes it much more difficult navigating in the southern hemisphere. The South Pole doesn't have a pole star. All right, but the southern hemisphere does have something that we don't have, and it's this beautiful thing here. Ooh, you can't see that quite well. All right, it's the Milky Way, and so since you can't see that very well, I'm going to go up to my grids and take off that equatorial grid and put on the galactic grid. All right, and so here, I'm going to pull to, let's say, here. All right, and now you can see we've got the plane of the Milky Way going across the center of it. And if I pan around on it, I actually have to work hard to pan around on it, simply because the panning is in equatorial coordinates, unfortunately, and not in galactic coordinates. So not quite so easy to do that panning in equatorial coordinates. All right. We've got galactic coordinates. Turn the page. All right. And so we've got the galactic coordinates. The one other coordinate system I can show you is the ecliptic coordinates, which are the coordinates of our solar system. So the center line on our solar system will be along here, and you'll see that yellow dot right there. If I hold on that was Saturn. All right, and there should be a couple other planets around here that will be along the ecliptic, which of course the ecliptic is the plane of Earth's orbit around the sun. Did you see Mars? Is that it? Yes, there's Mars. Very good. Good catch. Okay. So let's turn off the ecliptic grid. All right, we've got the constellations on here. Now I'm going to turn on the constellation boundaries. All right. Actually, which do we want to try? All right, there we go. Let's go over here to Orion, because Orion's a nice, easy one. We're going to turn on the constellation pictures. We'll start with the pictures. Okay, I'm going to turn off the boundaries. All right. So you can see Orion is the hunter here. Okay, we've got Taurus. He's fighting Taurus the bull. He's got his hunting dogs, Canis Major here, and Canis Minor here. And then, of course, he's got his fighting unicorn in between them. Monoceros is in there in between his hunting dogs. I don't think that was one of the original constellations, okay? You can go around, there's Gemini, okay? And if we go up here, we can see the Big Dipper, okay? And so the stars of the Big Dipper are part of Ursa Major, the Great Bear, and the handle of the Big Dipper is the big long tail of the bear. All right, how many of you have seen bears with big long tails? They only exist in the sky, okay? All normal bears have short, stubby tails. The bears with big, long tails only exist in the sky. And you can see the Little Dipper also has a nice, big, long tail for Ursa Minor. All right, so we'll get rid of those constellation figures. But we'll turn on the constellation boundaries. And I'm going to take off focused only. So you can see that what are the constellations really? Well, they are how we organize places on the sky, all right? They're a pattern, all right? And you can find things like Scorpius, which actually looks a little bit like a scorpion, and Sagittarius the archer, which looks a lot like a teapot, and not an archer. The teapot in Sagittarius is one of the best constellations, you know, best asterisms because it actually looks, it's something that really looks like something. But we can get to various constellations like that. What's that one? I don't know. Oh, wow, I can't even read it. I need my glasses. Uh-oh, I didn't bring my glasses with me. I can't read that. Can anybody read that? Oh, my gosh. Yeah. Okay, there's all sorts of constellations that you may have never heard of that you can go through. All right. One of the ones that we'll finish with is over here. Where do I want to finish? I want to finish over here on the nice pentagon type one. That's Aurigae there. All right, let's turn off these constellation figures and boundaries. All right, and take a look at our stars. All right, so we got our 88 constellations. You can do that. That's just panning around the night sky. Let's actually try doing something else. Does anybody know what this grouping of stars is called? Say it out loud. The Pleiades, okay? We're going to zoom into the Pleiades, okay? I'm taking my mouse wheel and zooming in. All right, the Pleiades is also known as the seven sisters. All right, tell me when you see more than 7 stars. Okay, you can see a lot more, okay? This is one of the coolest things about this software, zooming in and seeing incredible detail. It also shows you why Microsoft considered this a research project, okay? What they wanted to do was they wanted to handle terapixel data sets, right? And to get a terapixel image, you know, that's a huge, huge image. But the night sky covers a whole dome, and if you increase the resolution, you can have as many pixels as you want, okay? So to tile the entire night sky at resolutions like this, trillions of pixels. Okay, and especially since this was developed almost 10 years ago, 8 years ago, the computer doesn't need to hold all trillion pixels. All right, so when we zoom out, and I'm going to try and choose a random spot in the sky that I haven't been to before, okay, something like this, okay? Now, if you look over here in the lower right-hand corner, there's a bar here. As I zoom in, you might see it download new pixels as I zoom in. So Microsoft servers, all right, hold the data, and unfortunately our internet's too fast here, so that we don't get the long lag times we used to get in terms of downloading the pixels. All right? But I can zoom in anywhere in the night sky. There we go. You can see a little bit of a bar, right? I can zoom anywhere in the night sky and see it at incredible detail because Microsoft servers are out there serving the data up. All right? So you don't have to hold all trillion pixels on your computer, all right, in order to do this. All right? So we can go out and look at all of these interesting things. So let's see, here's another interesting thing over here. Let's zoom in on this. Anybody recognize what that smudge is? This is the Andromeda Galaxy, okay? This is the most distant thing the human eye, the unaided human eye can see, 2.5 million light years away. If I keep zooming in and keep zooming in, you can see the details. You can see the beautiful dust lanes, all right, that Margaret Meixer will tell you about next month. Gorgeous dust lanes in Andromeda. All right. I also wanted to illustrate another feature of it. Andromeda has 2 dwarf galaxies, all right, and I can never remember which one is which. So if you right-click on it, it tells you, no, that doesn't stop. That's not what it is. Right-click on it. Come on. There we go. That's Messier 110, okay? This is your finder scope, and if I zoom over here and right-click on this one, I should find that it's Messier 32, M32. All right, and that gives you information about it and so on. So that if you don't know what an object is in the sky, you can use the finder scope to take a look at it, okay? If you want to look for other things, that's some stars and a galaxy, we can go up to this search button up here, okay? And we can type in something. So let's go to Jupiter, okay? All right, and there's the Jupiter in the search, and I'm going to click on it. And you will notice that it will automatically pan across the sky and zoom in until it finds Jupiter. All right. Now, why did I have to search for Jupiter? Well, how come I didn't know where it was? I'm an astronomer. Why? It moves. The original Greek word planet is planetes, the wanderers on the sky, okay? Planets are handled differently, okay? They don't stay in the same place on the sky. All right, so we're looking at Jupiter here, okay? And we can zoom out a little bit. All right, and you'll notice that it has some companions, little dots around it. Well, that's going to give me an example to show off something else, this view menu. We've got the observing time. Now, what is this set to? This is set to 2008, February 21st. I don't know why that is, but we can change that. We can actually speed up time, so that's times 10, times 100, times 1,000, okay, and times 10,000. And now you see Jupiter move against the background stars, just as this young gentleman said it would. But you can also see the moons. Now I'm going to zoom in, okay. All right, and we can see not only the moon, we can see what's this, a black spot. That's a shadow of the moon that already went off. I'm going to try and slow this down and see if it's this shadow comes across. All right, it usually comes before or after, and it's not going to happen. So let's stop that. Since we missed it, I'm going to go backwards. All right. And so I wonder whether the shadow transit is due to this moon. Yeah, that's probably due to that moon. So they have full lighting in here that is calculated, all right, to do the moon transits when you're looking at Jupiter. Kind of cool. We can also use that time to look at something even more interesting, okay? So next year, okay, next year is 2017. Oops, let me zoom out because this is going to let me zoom out because it's going to go crazy on us if I sit there and do this with zoomed in. Okay, so next year, 2017, in August 21st at about 12 noon Eastern time, okay, I'm going to be in Grand Teton National Park, okay? So I need to set this up, and I'm going to say, all right, let's go to U.S. cities, all right, and we're going to drag all the way down bottom and get Wyoming, okay, and they don't have Grand Teton National Park here, but they do have the ski resort that's named Teton Village, okay? All right, okay. All right, and I'm going to view from this location. All right, and what do we notice? Well, we're looking at Jupiter, and the screen is blue there. That means Jupiter's below the horizon. What you've got here is you're looking at the horizon. All right, and I won't be looking at Jupiter then. Instead, I'm going to be looking at the sun on this date and I'm going to double click on this. We jump straight to the sun. All right, does anybody know what's going to happen August 21st, 2017? Just say it out loud. Total solar eclipse, and in Grand Teton National Park, you get 2.5 minutes of totality. So you see this object here? All right, that is the moon. So what we can do is go to our view menu. All right, and let me real time. All right, and let me speed this up a little bit. And we can watch the solar eclipse as it will occur as viewed from Grand Teton National Park on August 21st next year. And you can see that the programmer added in a little bit of bravura. He said, well, if the program calculates that it's a total solar eclipse, it'll show you the solar corona. Because that's what solar eclipses are supposed to be about, seeing the corona. All right? And then we can continue, and it will pass out of totality. All right? So hopefully if there are no clouds in Grand Teton National Park next summer, I and my family will be able to see that. If not, we'll just have to enjoy ourselves with the beautiful views in Yosemite and Yellowstone and Grand Teton. All right, so that's kind of cool. You can do that. Notice that this is viewing from a specific location. If you go out tonight, if you go up onto the observatory tonight, what will you see? Well, let's take a look. Where are we? Baltimore, Maryland. We'll say OK, and we'll set the time to now. All right, and then we're going to turn on something, another grid that helps you orient yourself, which is called the altitude azimuth grid. All right. So you can use the altitude azimuth grid to help plan your observing. So where are the markers? Hold on. Why aren't the grid markers on? Axis labels. There we go. I can't do anything without the axis labels. Okay, so here you can see 180 degrees, okay? That is south on the altitude azimuth grid. And if I turn on the constellations for you, you can see that tonight we've got Sagittarius here, Scorpius here, and Sagittarius down here. It's only in the summer that you're able to see down towards the galactic center. I'm going to actually speed up time just a little bit. There we go. So tonight, all right, if you want to see things near the galactic center, which is right about here, okay, Scorpius and Sagittarius, and tonight would be, the summer is a good time to do it. If, however, you look to the east, what are you going to find? You're going to find that summer triangle, Deneb, Vega, and Altair. If you look around to the west, what will you see? Well, you'll see Leo setting in the west. And of course, to the north, what will we see? Well, we'll see Cassiopeia low on the horizon, and we'll see the North Star. If we zoom in, you can see that the North Star is about 39 degrees above the horizon. What is our latitude here in Baltimore? About 39 degrees, okay? The North Star, height above the horizon, its altitude is the same as your latitude, okay? Altitude of the North Star equals latitude, all right? Or close enough, within a half a degree, because the North Star isn't there, all right? And the Big Dipper will actually be west of north tonight, okay? So you can use, I use this all the time in trying to plan observing. I did a cruise where I was giving talks during the day, and I did a little bit of observing at night. I used WorldWide telescope to help plan where we were going to be, where in the ocean, and then what would be up and what I could show the people at 10 o'clock at night when I did the nighttime tours for them. I also use it when I go visit my sister in Upper Michigan, because she's always asking me to show her, oh, show me what's up in the sky tonight, okay? And I need help when we're doing things like that. All right, so let's turn off that grid and move on, okay? So far, all I've really done for you is show you what we can see, basic constellations and stuff, human eye things. But what you really want to go when you're out observing, you plan an observing session, you want to see the deep sky objects, okay? So let's go search here, all right, and let's go here, and we'll type in M51, all right? M51 is also known as the Whirlpool Galaxy. Well, the software will automatically track across the night sky to M51, zoom in, and take a look at it. All right, so this is the Digitized Sky Survey image of Messier 51. That's kind of nice, right? But what's better than that? The Hubble image, of course. What building are you guys in? All right, so this is the Hubble image here. I click on that, and then I'm going to rotate it so I can make it nice and big. All right, and I zoom in a little bit. All right, and there you have the Hubble image. Now I can crossfade and say, okay, that's Hubble, and that's DSS. Space telescope, ground-based. Space telescope, right? But this isn't actually a fair comparison, okay? Because that Hubble image has 96 million pixels. My screen only has 2 million pixels. So in order to see them, I got to zoom in. And you know what? Just like there's a terapixel background sky image, there's all 96 million pixels in the software. So when I zoom in, you see the detail in the Hubble image, okay? Let me zoom in too far. Now you start to see the pixelization. Even Hubble has its limits, right? But I zoom back, okay? And there you get the Hubble image. Now we can do a fair comparison. So that's Hubble, and that's ground-based. That's Hubble. That's ground-based. Any questions as to why Hubble is so valuable? That one demo, it really gets everybody. Okay. So that's really cool, and we can see the Hubble. But Hubble's not the only space telescope up there. All right. You'll notice down in this tray down here, there's lots of images. What WWT automatically does is it finds all the images in your field of view and it puts them in the tray down bottom, okay, so that you can see them. So that is the Hubble image, and this one here is the Spitzer. I'm gonna, when I mouse over it, it's going to switch to the Spitzer. So Spitzer is infrared. You can see these dark dust lanes here. They are, what's called cool gas. They are dark with invisible light, but they're bright in infrared. So watch when I change from visible light to infrared light. Visible light, infrared light. It's like mirror images of the darkness becomes the light, okay? All right, so you can see that you can do multi-wavelength astronomy here, okay? It's not just Hubble and Spitzer, but lots of different other images. So let me go up here. Next thing I want to do is, how do you get to all these Hubble images? Well, this Explore tab gives you all these collections, okay? All right, and we're going to go to the one marked Hubble Studies. So if you want a Hubble image, there you go. We got quite a number of Hubble images for you to explore, and there's even another tab beyond this one, okay, of Hubble images out there. Plus, some of these Hubble images are in folders. You see that folder icon? So here are some nebulae. So it's nested in terms of these things. All right. So what are we going to see? All right. Let's take the Crab Nebula. Okay. So let's choose the Crab Nebula, and I'll pull this back up while it pans out. It zooms out, sorry. Pans across the sky to the Crab Nebula. And then zooms in. And this is a relatively low-resolution Hubble image, only 30 million or so pixels, but again, all of those pixels are there. I can zoom in and you can see the incredible detail. All right, this is the guts of a star blown across space at millions of miles an hour. This was observed by Chinese astronomers in 1054 to have exploded. All right, so this is a 1,000-year-old the star. You can see how it's just shredded as it's going across space. All right, so that is the Hubble image. That's visible light. Again, there is an infrared view. All right, visible, infrared. And you can see how the visible light is sort of like hair on the edge around the infrared view. And then we also have the X-ray view. Okay, and the X-ray view shows us the pulsar, the collapsed neutron star at the core. When this star exploded, the remnant collapsed into something called a neutron star that's spinning 30 times a second. Okay, it's about the size of the Baltimore Beltway. Okay, it's pure neutrons and it's spinning 30 times a second, putting off tremendous energy. And you can see some of that energy. Let me just click on this to keep that on. Putting off some tremendous energy. You can see jets coming out from that neutron star and the disk of material around it. So these images are all in the software. If you don't want Hubble images, I don't know why you wouldn't want them, but in case you want other telescopes, here are the Spitzer images here. Okay, lots of Spitzer images for you to look at. And here are the Chandra X-ray images. Lots, especially supernova remnants. Chandra is brilliant at supernova remnants to look there. So you've got these various image galleries from the space telescopes. You also have image galleries from other things. You have some astrophotographers who have provided their images for this. We have some radio telescope, just a few radio telescope observations. The National Optical Astronomy Observatories, the Gemini Observatory, also contribute their things. One other cool thing that they have are the all-sky surveys. All right, and before I do this, I'm going to back off and go here. So what we're seeing here is the digitized sky survey, which is a visible light view of the universe. Okay, but what if we looked at it in a dust map? All right, getting that warm gas to glow. Well, then it would look like this. That is the all-sky of the dust map. Okay, and you can see that it distinctly shows you the plane of the Milky Way. All right, and where am I trying to get to? I want to get. Yeah, I know. Following the Milky Way is not as easy as is not an easy thing because the panning is in ecliptic coordinates, not galactic coordinates.
Dr. Zorn, can I ask a quick question?
Sure, go ahead.
Say what this is again. If I'm hearing you correctly. Dust?
This is dust. This is the warm gas in the Milky Way, mostly confined to the center plane of the disk of the galaxy. Okay. All right. Now, if you want to see where stars form, well, you look in hydrogen alpha. So if we go from here, All right, that's the visible light. Let me go back to the visible light. And if we want to see where stars form, we go here in hydrogen alpha, and here you can see all these star-forming regions around here. All right, and if this is actually visible light, but it is the energy emitted by hydrogen. Okay, and let's take a look at this. Right? Does anybody know? You see that there? All right. If we go to visible light, that's the constellation of Orion. There's a lot of star formation in Orion that shows up. This is called Barnard's Loop. Okay, you can see a tremendous amount of energy being put off into this 3,000 degree gas that radiates at hydrogen alpha. So this is actually what astronomers have done over the past century. So we've gone from visible light exploration of the universe to visible light plus infrared plus X-ray plus microwave, all sorts of different things. And this kind of multi-wavelength astronomy is possible with WorldWide telescope. The one more I'm going to show you is the largest one ever. It actually doesn't cover the full sky. It's called the Glimpse 360 survey. All right, and I'm going to click on that. Actually, you know what I'm going to do? Hold on. I'm going to click on a black background and then glimpse. Okay, so let me rotate this so that the galactic plane is flat. This is the galactic center. And this was done by the Spitzer. It's a survey done by Spitzer. And I can keep going in and going in and going in until you finally see the resolution of it. Okay, this is a several billion pixel image that we're examining here. Okay, and I want to go over to these regions right here and take a look at them. All right, so if I look at that in infrared, you can see there's all sorts of cool stuff. All right, where in the infrared, whereas if I then pan back to the visible light, you've got that. And the infrared shows you so much more. All right, sometimes visible light, there's more to the universe than meets the eye. All right, this one here, same sort of thing. The infrared is, the visible light is relatively constrained. The infrared shows you an incredible panoply of things. And then finally, these two knots down here. I was playing with it this afternoon, and I saw that, wait a minute, where are they? There they are. They're just not there in the visible light survey. All right? So what are you doing? You are seeing the universe in a whole new light. All right? That's what this the software allows you to do. Hey, we got to take the puns when they come, all right? All right. I will also note that these surveys are available down here when you look at the sky as a sky background. Okay, so there's lots of these surveys available here so that you can choose them. We were just using the digitized sky survey for our work. All right, now I have to choose an image just to get rid of the glimpse survey, otherwise it will not get rid of it. Okay, so you got these cool data, right? What if you want to add your own image? So if I go to the search bar up here, all right, Hubble released a cool image of the Bubble Nebula. All right, here is an old Hubble image of the Bubble Nebula. I'm going to zoom in on it. Okay, and this is the old WIF Pic 2. You can see the stair-step shape to it, okay? That image is of, here's the whole bubble, and that image only covers partial of it. We released a cool new image that covers the whole bubble, but you know what? It's not in the software. How are we going to get it in? Well, let's go up to the Explore menu. We'll click on that arrow underneath it and say, Open Astronomical Image. All right, and we'll go here to this directory. We'll find this Bubble Nebula image right here, and we'll open. All right? Boom. That image was tagged with AVM metadata that told WorldWide Telescope where it existed on the sky, and WWT automatically added it in at its correct place in the sky. So now I can crossfade out, and you can see the DSS version of the bubble come in and see the Hubble image, and this Hubble image is 70 million pixels, which is why it took a little while. And we can go in and see some of the details in here. All right, some of the cool details. And then it's always fun to do the crossfade to say, here's what we see from the ground, and here's what Hubble sees. I know, I'll never get tired of doing that. Yeah, there we go, right? That's Hubble, that's the ground, and that's Hubble. All right, so that's how the American Astronomical Society is going to bring in these research-level images into the software. By having them tagged with coordinates, it can automatically put them on across the sky. You can take your infrared and your X-ray and your microwave image of the same region of the sky. They'll automatically be registered one to another. You can do this multi-wavelength comparison. All right, but wait, there's more. Supposing you have not all astronomy data is images. What if you have data sets that you want to bring it in? Well, for that, I need to actually jump out of the program for a second. Go here and go here. And I need to open something I should have opened before I started, the Excel file of exoplanets. All right? So this is an Excel file that has extrasolar planets, characteristics of the extrasolar planets, and then the star and the RA index of the star, so the coordinates of the star. And all of this is here in a simple Excel file. But there is a WWT plugin for Excel that allows us to visualize the selection. So I can click View in WWT. All right, and it will pull out, it adds a new layer for this catalog that has 652 exoplanets in it. All right, and if you want to know, why is it zooming in on that star? That's not, obviously that's a special exoplanet. Which one is it? Let's right click on it to find out. That one is 11 Coma Berenices. Oh, yeah, one of my favorites. So these yellow circles show you where there are stars with confirmed exoplanets, okay, across the night sky. And the answer is, where do they exist on the night sky? They are everywhere, okay? This simple demonstration shows you can get a data table, bring it in, register it with the night sky, and examine your data that way as well. So this is what we're going to do with the Astrophysical Journal. We'll have these tables, we'll have these images, we'll have this stuff. We'll be able to pull them into this piece of software so that anybody who reads your journal article can then visualize your data. Okay. So that gets us through with our night sky browsing. Let me turn that off. You think we're done with the tour, right? We're only about halfway through, actually, because there's so much cool stuff, okay? I said around the universe in 80 ways, but the next stuff goes a little bit quicker. So in the lower right-hand corner, there's this Look At button, okay? And we've been on the sky the whole time. It also has an Earth view, all right? So this is like your digital Earth that you've seen, okay? All right, and if we zoom in to southwestern United States, and we start to zoom in and go to one of my favorite spots. Okay. Oh, wow, the shine on this is not working. So, you know what I'm going to do? I'm going to show you something. All right, if we're trying to find the Grand Canyon, right, we can go to the street view of it, right? That's why it wasn't working, because we need to be over here. There we go. All right, so now we got Grand Canyon National Park. Okay, we're going to span over here. There's Grand Canyon Village. All right, we'll get rid of the street view, and we'll go back to the aerial view. All right, and we'll zoom in. Okay, so here is Grand Canyon National Park, and this is the south rim. All right. And my wife, who's sitting in the audience, will remember this. This is the start of the Bright Angel Trail, okay, right here in the parking lot. Remember that, honey? Okay. And then when you take, what you really want to do is you want to take the view from that. And you can virtually view the Grand Canyon, okay? How cool is that, right? All right, and so what you can actually do is I'm going to pull back, all right? Pull back, and you can follow the that's a little bit too far back. You can follow the Bright Angel Trail, all right, as it goes down into the canyon. All right, I'm going to pull over here, and you can follow it and pull back. Pull back, come on. There we go. You start to see, I need to rotate. There we go. That's better. Now you can see the Bright Angel Trail as it goes down into the canyon. All right, and I pull back, and you can see we descend into the canyon. All right, I'm going to rotate around. Pull it up. All right, so we're going to follow that Bright Angel Trail down into the canyon. All right, and we're going to take the west path that leads to this promontory here. Okay. Well, we'll go right about here. We'll zoom in. We'll zoom in a little bit. And from here, this is a gorgeous view of the Grand Canyon. See? I just saved you all sorts of vacation dollars. All right. As we're looking back up, and my wife gave out right about there. We took river rafting down through the Grand Canyon, and then the hike out is 10 miles, 9 miles in length, and 1 mile of vertical. And I swear the last mile or two was just really tough for her. All right, but this was very shortly after we got married, and we were gung-ho to do all sorts of fun things. So, you know, that's a fond memory for us there. We love the Grand Canyon there. All right. So you can see things like that. Let's see, let's pull it up, and we'll pull out. All right, let's spin around here so we can get these things in. Yes, the Colorado River made all of that. Okay. You could go visit Area 51 if they haven't erased it, you know. And so here we can go to the hybrid, okay. All right, and so if you wanted to see where things were, I guess I have to spin around to north up in order to see that. And let me tilt down. You can see here, I highly suggest visiting over here. This is Zion National Park. And up here, Bryce Canyon National Park, another one of our favorite places to visit. And then when you get tired, you can go over here to Vegas. That's one of the great things. I mean, there's also like Canyonlands. Yeah, there we go. Let me pull back just a little bit. Oops, not too much. Canyonlands National Park, Coral Reef National Park, Arches National Park. Amazing sort of stuff to look in this area. And when you get tired, you can go to Las Vegas. And if you really need to find Las Vegas, well, then you just turn out the lights. So we can also do the Earth at night. Boom, where's Vegas? Yeah, I think you could find Vegas pretty darn easily. All right. And I always like this Earth at Night map. You can really see the structure in the Midwest of all of the streets and highways. But the coolest thing is actually over here in Korea. All right? All right, if we zoom in. All right, this is North Korea up here. This is Pyongyang. All right, here is the border. This is Seoul. All right? It's absolutely amazing, the contrast between North and South Korea here. So kind of a fun thing to do with the Earth at night. So basically it has an Earth mode that allows you to look at the Earth and actually have 3D modeling. If it's got Earth, it also has the other planets. All right, the most interesting of them is Mars. All right, so here is Mars. And as we pan around Mars, we'll come eventually. come across the Grand Canyon of Mars, which is down here. All right, so I flew you into the Grand Canyon on Earth. All right, so let me go down to the Grand Canyon of Mars, which is called Valles Marineris. All right, and you can have the 3D structure of Valles Marineris as well, although it's not quite as impressive because it's simply too big. All right, if I take that, pull back, and if I go from one end of Valles Marineris to the other, I'm crossing from Los Angeles to Washington, D.C. It's about 3,000 miles across. Other fun thing to do on Mars is to go up to the Tharsis Plateau. You can see the three shield volcanoes here, as well as this volcano here. All right, this is Olympus Mons, the largest volcano in the solar system. The area covered by it is as large as this entire state of Arizona. And if we tilt it down, it doesn't look like that big of a bump, okay, but it's 2 to 3 times higher than Everest. Yeah, across is the largest volcano in the solar system, and you can see the details of that. All right, so where else are we going here? All right, okay, one more thing. The other planets are not so great. Whoops, sorry. But the moon is fun. All right, where is the moon? There's the moon. All right, this is the far side of the moon. The moon also has data on its various features, and I want to go into this Tycho crater here. You've all seen that this is at the moon. Look at, there's this crater down the bottom of the moon. All right, if we zoom in on it, okay, also has elevation data, so you can see the craters on the moon. All right, cool stuff there. All right, pulling out, let's see. If we just do any of the other ones, the Io is really cool, but these are all just flat spheres. They don't have 3D data associated with them. The other one that they threw in just for fun is the Mandelbrot set. Mandelbrot set is a fractal, okay? So I'm just going to pick a random spot on it, all right? And this is mathematically recalculating as I zoom in, okay? The features are recalculating of the fractal, all right? It's generated by a simple mathematical formula, and it's recalculating as you zoom in. So this is a fractal, all right? It's a mathematically generated terrain. Developed, and so they could go that effectively infinitely deep, although there is a pixel scale that they have to obey. All right, and so you can get all sorts of crazy resolution using the Mandelbrot set. All right, so those are the planets. It also has a panorama mode. All right, and I'm not going to use that one. What am I going to use? Oh, I'm going to use the Apollo 11. So the landing on the moon. All right, we have a classic shots from various Apollo missions, and of course we have the flag there. All right. The other one I wanted to do was, oh yeah, Shorty Crater. Okay, this one's cool because we've got a crater here, right? And then you get what's the astronauts called the magnificent desolation of the moon. All right, there's just nothing. All right, and I can zoom in and show you that just there's a whole lot of nothing out there. And then there's just this one little lunar rover. Okay? Just sitting out there, okay? So when you're on the moon, you are literally alone on the moon. All right? So they take the shots of that. You can also go visit Mars, okay? And if you want to be the Sojourner rover, and move around the rock garden while it's taking various shots and stitching them together into a panorama, you get the many rovers shot here. With this is the Mars Pathfinder mission and the Sojourner rover and the Twin Peaks in the background. Let me just show you that there are a tremendous number of these Mars ones, including this one from McMurdo, which is in anaglyph 3D. So you put on your red-green anaglyph glasses, and you can see Mars in 3D. The other one I was thinking, and we can also do this for our own planet, but we don't have actually some really exciting ones. We've just got this shot of these telescopes up at the top of Mauna Kea. All right, so this is kind of cool. These are all the telescopes at the top of Mauna Kea, but it doesn't have any cool shot of the looking out over the edge and seeing down from 14,000 feet. So stuff like that. Panorama mode, okay? All right, finally, we get to the solar system mode, where we get to see the solar system in 3D. All right, so this is the mode that everyone loves, that I leave it for last, okay? And you can say one of these, here are these orbits, one of these things is not like the others. Anybody have a guess what this is? Pluto. The programmer still loves Pluto, wants it to still be a planet. He can't accept reality. So if we look at it like this, all right, we go over to the layer manager. All right, I will show you what reality is. Here are the asteroids and other minor planets. Okay, all right. In the outer solar system, beyond the orbit of Neptune, which is this blue one, you can see all of these thousands of objects out here that are out beyond Neptune, have tilted orbits, have elliptical orbits, and are in other ways just like Pluto. Pluto's family is called the Kuiper Belt. Okay? And if we zoom in towards the center, you can see that we come in and we can see the main asteroid belt in here. We can also see the Trojan asteroids that are in the gravitational pull of Jupiter. All right, and I'm going to turn off those asteroids because there are, about 400,000 of them, so they can slow things down. All right, zoom in a little bit further. All right, and we've got the sun here. All right, and let me just check one thing. Let me pull the planet size to actual, and let's go to Earth. So I click on Earth here, and the software automatically takes me to Earth. All right, we're running out of time, so I can only show you so much. I need to get to the tours that we're doing here. All right, so here is Earth, but I wanted to show you something really special about Earth. You can see that they've got the lighting, okay? So let us go to, we are going to go to the View menu, and we're going to take the observing time to be 2017 8/21 again. And I'm going to take a look at this. I'm going to say OK. And on August 21st, 2017, there's the path of the solar eclipse going across the United States. How cool is that? You've never seen a solar eclipse in 3D, have you? All right, let's pull that back. All right, I will pause that. We'll move around behind Earth. And if we look towards the sun, you can see just a tiny little black dot. I can't get it exactly matched because I have to be on Earth to do that. All right, but if I pull up and zoom out, you can see Earth, Moon, and Sun. I can continue time, move it faster, and we can watch the Moon orbit around Earth. While we're following Earth, I can pause it here, all right? And if the Moon is 90 degrees away from the Sun, what phase should it be on? First quarter moon. It's hard to see, so I will take the planet size and I'll make it larger. And I'll back off a little bit. And now you can see that from the Earth, the moon is indeed in first quarter moon. All right, you can teach the phases of the moon with this software, seeing it in 3D and seeing the geometrical constructions. All right, now I don't have time, so I'm going to jump to the sun. All right, and let's start our big traverse. All right, first of all, got to turn off the constellations because they're about to make no sense whatsoever. All right, and I can turn on time. We'll skip time. All right, we can pull out and see the solar system and say goodbye to the solar system and continue further, and you see that the stars are also in 3D. Okay, this is the Hipparcos star catalog. All right, we zoom out. Now you're not going to be able to see this. I'm going to see it on my screen, but the stars become this little gray blob here, and then I'm going to see that the gray blob is about twice the size of that plus sign. It's about here, okay? Those are all the stars of the Hipparcos catalog, 100,000 stars. And let me turn on the Milky Way. And if we zoom that up, we rotate and I pull out, you can see that all the stars in the Hipparcos catalog are just a pepperoni on the pizza that is the Milky Way. All right? Very, very small. Every star you see in the night sky is within a pepperoni on the pizza that is the Milky Way. But can we go further? Of course, I wouldn't ask the question otherwise. We can go out to come on, wake up. We can go out to the galaxies of the Sloan Digital Sky Survey. I back off. All right, I know I'm on the wrong side of the Milky Way to do this, so I'm going to spin around over here. You can see these 3 stripes here. Oh, you can't see those 3 stripes there. Strike that. All right. If you look on the monitors on the side, you can see those 3 stripes. That is the structure of the Sloan Digital Sky Survey, but you can also see the galaxies of them. Every dot you're seeing here, there we go, is a galaxy. And notice that since we're still centered on the sun, the torque, the lever arm is huge, and so everything spins very quickly. If I pull out, I can show you the whole Sloan Digital Sky Survey. You can see they covered a volume over here, and they just covered 3 slices of the sky over here. All right? And yet, you think that's big. It's not big because I'm going to show you the scale of the entire observable universe with the cosmic microwave background. All right? And you can see, compared to the scale of the entire universe, the Sloan Digital Sky Survey doesn't go very far. All right? So are we ready to go home? All we have to do is click that button of Earth, and here we go, flying through the cosmic microwave background into the Sloan Digital Sky Survey, all the way down to the Milky Way, through the stars, to our solar system, past the sun, and we end up at home. All right. All right, if you will give me just 5 more minutes, I have to show you one of the coolest feature of this thing that, of course, I leave for last. All right, you'll notice that there is a telescope tab up here. You can connect this software to your telescope. There's a community tab up here. You can share your things amongst the community. But the most powerful tab is this one right here, which is the Guided Tours tab. So you can have, on a WorldWide telescope, you can have an overview, which will tell you a lot of what I just showed you. You can have features like, using the image crossfade or making a constellation figures. You can make your own constellation figures. They have tours on how to create tours, working with interactive tours. They have tours for educators, okay? They also have tours that tell you about the universe. So, for example, let's pick this one by Dr. Frank Summers. I know him. He created a tour. We hit the button. It downloads it from the server.
Welcome. I'm Dr. Frank Summers of the Space Telescope Science Institute. Let me show you one of my favorite places in Hubble's universe. We begin at the constellation of Orion.
Okay, you're taking too long to get to the pretty pictures. I'm going to stop that. And you can see what the tour is all these slides up here. It looks sort of like PowerPoint, but for the night sky. All right, and so I'm going to slide over here and say, where are the pretty pictures, Frank? Oh, look, there they are. They start here. So I click it here. I pick up the tour again.
This image from the Hubble Space Telescope captures the nebula in amazing detail. The group of hot young stars near the top provide the stellar winds and the high-energy radiation that carve the bowl shape of the nebula.
Overlays to put them on, drop images in.
An earlier Hubble image showed the details of the region near these hot young stars.
We've got music in the background, narration. It seems to be a bit fuzzing today. Sorry about that. And these zooms are just wonderful. Anything you can do live, you can do in a tour.
The 4 bright stars are called the trapezium. These stars
All
are
right, and you can pause it, and because you are inside the software, you can go around and do all sorts of things within it. You are live in the software, and then you can pick the tour back up, okay? All right, these tours are available to you. Let's see. I will just mention a couple other tours. All right, you should watch my Orion Nebula tour. It's about 6 minutes. There are tours by other very smart people, like the Chandra Crab Nebula tour by Megan Watsky. If we go up and look in the galaxies, let's see, Robert Hurt, there we go. Robert Hurt had a M82 tour. There's all sorts of people able to do cool tours, all right? But, as I like to say, it's so easy, even an astrophysicist can do it, but you don't need to be an astrophysicist to do it. All right, let me go up to this Explore tab, and I'll say Open a Tour, all right? And I will go to tour that was created by that 16-year-old right there who had not touched the software. 2 weeks ago, she had not touched the software. As of today, you've created 9 tours, I counted. You created 9 tours. She's working with me as an intern for the summer, okay? This tour, this is not the tour you specified, sorry, but I didn't have time to load that. I forgot to load it, all right? So this is one of her tours that she's making for the Hubble Space Telescope, looking at the Sombrero Galaxy, all right? It's about a 20 or 30 slide tour, all right, where she brings us into the Sombrero Galaxy, all right? And slowly fades in the Hubble image, which I think we wanted it to come in earlier, but the software does something funky these days. All right. And then goes through the various features of it. All right. And I got to emphasize, this is by someone who had no experience with the software as of 2 weeks ago. So, I mean, and you did this one in the first 2 days, right? Yeah, so in the first 2 days. That's my niece, Uni Park, who was able to do this. Okay, kind of cool stuff. All right. Now let me show you some other cool things you can do with the tours. I created a tour just for the fun for you guys, especially for you guys tonight, to show you some of the demos. All right. And the first thing I'm going to do is take you into Mons Hadley Delta on the moon. Anybody know Mons Hadley Delta? It's up in the Alps on the moon, which are actually at that ring of that crater. All right. So we zoom in, and there's Hadley Reel there, that little meandering river-like feature. That's Hadley Reel. That's what was studied by the Apollo 15 astronauts. Matter of fact, this plane here in front of us was where the Apollo 15 mission landed on the moon. And the Apollo 15 astronauts took one of the most famous NASA pictures ever taken. From somewhere around here, they got that picture. Able to see where, basically an approximation of where on the moon you get this, all right? Now, if you look at this tour, you can see that it took a bunch of slides to get there. One of the features that they have is a timeline. So if I show you the timeline for this slide, and let me zoom, whoops. You can see that that the timeline has various dots in it, okay? So if I preview the tour from here, all right, I'm able to, in one single slide, do this entire motion. Come into Baltimore. and see Ravens Stadium, all right? Able to pull out, always bring the hometown team into it. Pull back and we can see the inner harbor, including Fort McHenry down at the bottom. All right, all of the things. Come north along 83, and we find the Johns Hopkins University. Come on down, and we see the Space Telescope Science Institute. All right? So through the use of timelines, I was able to do that entire thing in that one slide. All right? And finally, we're going to go to the heart of Earth, which was a cute little thing that Jonathan Fay, the programmer, tweeted about. Where does it say? Come on. So in looking at Earth, okay, they have the standard Earth mode, but they also have a cutaway mode where you can examine the interior of Earth. All right, and so they take a quarter of the globe and they show you the core of Earth. What Jonathan tweeted in February was that if you notice that you tilt it like this, you get to the heart of Earth. Okay, so that's just one of the fun little things that we can do. If we had time, which we don't, I would make a tour live for you here. The last thing I'm going to show you, I have a touch screen there. Most of your, there are more touchscreen devices when we talk about iPads and tablets being sold than desktops and laptops combined. So you want to be able to use it on a touchscreen device, right? Well, I created an interactive tour just to test this out. So if we click on any one of these, okay? Click on an image. We're going to take this one. I'm going to click on it, all right? And it's an interactive tour allowing you could touch that on the touch screen over here, which I've run out of time. It goes all around the sky, goes in to find that image, brings in the Hubble image, and tells you about it. Okay? All right? You can also click on this full press release in a web browser, and it will pop open a web browser giving you the Hubble press release for that image. Okay? Kill that. Click, touch next. All right? And it will then go around it. So with these tours, they don't have to be just playback. They can actually involve touches to move across. And we pull into one of my favorite images of 2013, the Horsehead Nebula in infrared. Okay? And that was one of the horsehead of a different color was one of my favorite press releases. All right? I will fire up this touchscreen down here. If you would like to play a little bit with WorldWide Telescope on the touchscreen at the end afterwards, you can come down. I can show you some stuff. You can play with it and have a look at the software. So you can see that as I've shown you, there are probably more than 80 ways that you can go around the universe with WorldWide Telescope. Thank you for your attention tonight. Question?
You mentioned planetarium use.
Planetarium use, yes.
Is it the same package?
Same package. Let me just show you one thing. If I go to the View menu, there is Full Dome, and we can view this in a dome. You can zoom around things on a dome. It's in use at the Adler Planetarium, as I said, and other places. So, yeah, it can be used in a dome. You can create dome shows in the software. All right. Duncan, are you here? Where's Duncan? Duncan, we'll take you across the street to the telescope if you so wish. Duncan, why don't you come on down there? I'll fire up the computer. All right, it's after 9:30, so head on home. Have a good time. See you next month.
How long did it take everyone to code this thing?